byte, right? And we use the interrupt to trigger all that. So this is an example right here. In our time delay, we're using an integer value, which is 16 bits. But we only can write 8 bits at a time. So what we did was we would take the value and AND it with a 0FF. So it's pretty much, these zeros are going to cancel all these 8 bits over here. And this is all 1. So it'll keep these values, and then we store it, we'll write it as a chart, which is 8 bits. And we store these 8 bits into the EEPROM location 00. So we still have these other bits that we need, because it's all the information we need. So we do the same process. Well, we would shift all these bits over 8 places, and we remove these first 8, and all these others we shift over, and that's the ones we needed to complete the number. And once again, we take that data and save it in EEPROM location 1. And it would take 3 milliseconds to write. And this is the whole idea right here. Like, the idea is whenever the LED is running, we want to keep where it is in its lifespan. So the whole idea is when we kill the power, we need to know how long it was on and everything. So this is the circuit we use, a hysteresis for the internal comparator. The PIC had 2 of them, like Dan mentioned earlier. And it's kind of backwards the way this guy worked. Everything centered around the sensor needed 2.9 volts to run. So for our sheet, and Russell sent us, they gave us 3.6. And what we did was we ran a diode, and it drops 0.7, so we have 2.9 of DCC. And we used the capacitor to filter it out. But the way it worked, though, when it's on, and this is the internal fixed voltage reference module, which is 2 volts. It would sit right here. So whenever the device was on, the negative portion of the comparator was higher than the positive. So normally it would be a low out. But that's the way it was designed. I'm assuming they did that, say, prior. So the output would actually be a high, so it would be on. And that interrupt I mentioned earlier, it's edge triggered. It gets triggered when it sees the pulse drop down versus level triggered. So whenever we kill the power, this would go down to 0, and then this guy would flip and turn high and trip the interrupt. And when the interrupt was tripped, then we do that whole data recovery or data saving process I mentioned earlier. And that was a pretty nice device, actually, internal. And this is our schematic. Just want to show an idea of what we use with our PIC, our LCD, and I mean, I don't want to go over that too much. And this is the whole general idea, the flow. The PIC was is the microcontroller in the middle. And so whenever we turn on the device, we would also flush out the EEPROM. We set everything to 0. And once we turn it on, everything we powered up, and we start measuring data from the sensor. And this is the LED module feeding, the light, obviously. And then we would take that data, convert that analog data to digital, and send it over to our controller I2C. And it would just constantly do that. And the whole idea is to sample it once a month. And once we reach that threshold, the 70 or 50% of the light, we would trigger another separate LED, like Dan mentioned earlier, to notify the user that it's it's done. So that's the whole process, right? And we also have a power relay, and then down the line we use Bluetooth to give the user an option to turn the light on and off wirelessly and everything. That's basically the whole idea. And what was nice about the PIC, like Dan mentioned earlier, it has different oscillator speeds, and we had to use that because when we run our main code, these are time delay. We wanted the slowest oscillator so we can get the most bang for our buck in our iteration. But when we use I2C, we had to boost it up to 16 megahertz to generate the 400 kilohertz baud rate with the I2C. So we're constantly shifting the oscillator up and down, speeding it up, slowing it down. And EEPROM Right's got a problem with that. Like I said, with the MP lab, it had a feature where you can click and reach the EEPROM data. We were trying to do it with our LCD screen, seeing what was in there, and we were having problems. But we eventually got that to work once we were able to use that device in the MP lab. And we were using the interrupt I was mentioning earlier. When I was writing the code, when we were writing the code for it, we were having trouble triggering it. And the thing is, we were going to try to interrupt, and you're supposed to clear this flag first, but we didn't realize that, and we were doing the last step of the interrupt, and it just took like a lot of time, and it just one placement of a silly little device. But we figured it out finally. And like Dan mentioned earlier, the sensors are very fragile. We bumped them a couple times, and they would just break off. And like I said earlier, the light sensor was pretty much the guy that controlled the power for everybody and for the I2C. So we had to base everything around the 2.9 volts. And we were doing I2C. We had another problem with that. We were monitoring the wrong receive flag, and we had trouble to rework up the next slide to show it. So So this is what we had in our data sheet right here, and I'll just cover the basic thing. Right? This is the data frame and the clock, and this is the bit that I was monitoring right here. We were monitoring, and whenever you would transmit, receive, or anything, this interrupt will be triggered. So we were trying to keep everything uniform and keep it simple. But for the receive section, you can see the receive data right here. This interrupt is supposed to be tripped, but it was not working. And it took us a while to figure out why it wasn't working. That was the problem. And then eventually, we ended up monitoring the receive enable bit. And we got through that. It took some time right there. Just one little bit, but it worked for everything else. And that was kind of like stumped us for a while.
So Bluetooth actually was expansion to our project. So as all of you know, that Bluetooth actually works at a short range. Bluetooth have its own specific frequency. All devices that works in a radio frequency basically have its own specific bandwidth. So for our Bluetooth, it works at from 2.4 to 2.485 gigahertz range, which is also the IEEE standard for the Bluetooth. And when we were looking for Bluetooth, there was several options that we found. Some of them actually have 4 or 5 pins, and the one we chose is HC05, which had 6 pins. The reason we chose this because it had a pin for a key, which we needed to go into AT command and change the baud rate and change the name and so on.
This is just a basic block diagram of our entire project that shows how our microcontroller unit and the Android application communicate with each other and control the entire thing. For example, the microcontroller takes the data from the light sensor and sends it through the Bluetooth to our Android application, which receives it and shows the status. And our Android application has another feature: it can remotely turn on and off any electrical device. And for that, it sends the data to microcontroller, and microcontroller controls a relay to activate or deactivate any electrical device in the room. It can so.
All right, like we have another picture of the HC05. Like Rashid had said, we mentioned this is the key pin that he was talking about, which we sent specific AT commands to change the name of it and named it SUNY Newpal/Selux Lighting, and then we also changed the password of it. We didn't change the baud rate that much because we wanted to stay with the 9600. That worked pretty well for everybody. It was kind of general, and that's what we're trying to answer for us. And then there's over 30 different AT commands to change everything you want to do, from baud rates to all, like I said, the names, the passwords, to its actual address and everything. But we didn't need to do any of that kind of stuff. It's pretty low power, only 93 milliwatts at pairing, which is the most high power device between that and actually sharing information. And like the communication is only about 25 milliwatts, which worked out pretty well. And this device we chose it because you can do UART communication to it, SPI communication to it, or USB. We ended up doing UART because that's what it actually came pre-soldered on the surface mount board for, and it worked out nicely. All right, program.
Yeah, there's 2 methods when you get the device. When you want to change, do an AT command, and like Dan mentioned, we changed the name and the password. And the first way to do it in AT mode 1, which results in a 9600 of the baud rate, is set the key pin low, make sure the device is powered off, set the key pin low, turn it on, and then connect the key to the VCC, and then you'll be able to, and the way we did it, we communicated and changed things with UART, and we changed the name and passkey. The second way is to power the device off and connect the key pin to the VCC, then power it up, and it'll be and then obviously the default baud rate. But like I said, we wanted to keep 9600. We didn't really weren't pressing for speed or anything, and it worked out just fine. And in order to communicate, like so, we use UART, and I'll just cover a couple of things. Before you transmit data or anything, you have to convert data to ASCII characters. And the character framing is like when you transmit the data, there's a certain amount of bits, and they have to be set in position a certain way. And the start bit has to be low, and then you can see your 8 data bits can be higher, whatever you high or low, and it has to end. The stop bit has to be a 1. And then it has 2 pins, transmit and receive. It does have more if you want to do like RS-232, but we didn't really need that application. We just wanted to program a Bluetooth module, and this is only 2 pins we have to use to make it. And this is an example of this is an ASCII, this is a 1, but it's converted to ASCII 1. And you can see right here, this is the start rate, which is a low, a 1, and these 4 bits represent the first 4 bits of the data. And right here, this is the stop at where it goes high. And generally it's the same, the whole idea was the same, we kept everything, but this is for the Bluetooth expansion, and we just added the Bluetooth module, and it was UART, can talk back and forth. And when we actually got the Bluetooth module, it took us a while to realize that the printing on the back of the board, it was labeling the pins, the transmit and receive pin was backwards. So it took us a while to figure out, because we would send something to it, and nothing was happening, so we took an oscilloscope probe and did some signal tracing. We went up to where the microcontroller was sending out the signal, seen the data there, went to the Bluetooth device, checked it there, it was there, and but nothing was happening. So we went to the actual soldering point, and the data wasn't there, and we finally put 2 and 2 together and realized that things were flipped on the board itself. And our biggest problem with that, we were transmitting fine, we transmitted data perfectly, but we couldn't receive, we would receive stuff, and it was just, we couldn't do anything, because when we used the Bluetooth device, we wanted to send like commands like status and change stuff. So we're using a case switch once the data came in, and we would trip and interrupt. When we receive something, we would trip and interrupt and go over there and use that case switch. But our problem was, like I mentioned earlier, we're using a slow oscillator to run all our code. And whenever we would receive something, we would trip and interrupt. And when interrupt would be tripped, the oscillator was on the slowest setting, but it needed to be on 8 megahertz so it can keep the 9600 baud rate. So when the data would come in, it would be a framing error, and the data would be shifted over. Instead of a 1 coming over, it'd be a A or B. And we didn't realize that we had to keep our baud rate, and that took us like a day to figure it out. Once we figured that out, we could send different letters and it would work out. Our case switch would work perfectly.
This is just the basic working set that we use, because we're working for a single project, but we're still at 2 different groups, so we had to have 2 different working environment for each of us. Even though we didn't program anything from microcontroller, but we still needed a microcontroller because we started to design the Android application before the feeder I2C, so we needed to check that if our Android application is working with a microcontroller or not. The reason that we used designing a microcontroller code is so that we can verify that it's talking with one microcontroller, so that it can talk to any other microcontroller in the market.
Alright, so when we're actually doing Android, we had different options to choose different IDEs. One option was the Eclipse environment, which is based on Java and XML, and there's other programs that uses Python and other languages. We chose the Eclipse environment because when you have Java, you have more control over the code and everything. With Python, it's actually a little bit complicated. I mean, the programming is easy, but it's a little bit complicated when you are dealing with graphical stuff. So that's the reason we chose Eclipse. This is just a picture of the Eclipse environment. It's actually really easy. It's well organized. It's easy to use. When you're actually making your code, if you type anything wrong, it actually tell you what you're doing wrong, and it give you help basically. So it actually worked out pretty well for us.
When you design for Android operating system, one of the important things to know is the life cycle of an Android application, how it works. As any other application, whenever you turn on an Android application, it launches activity, which creates several methods. These all are the methods. Some of them are predefined, that all of the application will have those methods. For example, the onCreate method. This is pretty basic to any application. It initializes all the variables, buttons, and text views in any application that you're going to use in future. Then the next method is onStart. It just follows after onCreate. It goes to onStart. It's you can put some code in there. You don't have to. If you don't put any code in there, it's okay. It's still okay. And onResume is just another method. You can put your code in there, or if you don't put some code, it still will work fine. But your main code will sit in here, activity running. You have your main code that will run all of your things. Now, after that, after your main activity, you have your on-pause activity. What it does, whenever you press your home button in any Android application, it holds the application to pause. It's not running, but it's holding the memory, so that whenever you turn it on, it will start from where you stop it. But the on-pause has one method it called it has a method built into it. Whenever you need more memory for your Android application, it will kill the application that is on pause, so that it can clear more memory for other application and it can run smoothly. The on stop and on destroy are basically the method that telling the application to kill itself or destroy, so that it don't use unnecessary memory in the phone, so that other application can use more memory and run smoothly. To code for Android, some of the things is very important. Android application, for example, the knowledge of Android lifecycle, which helps you understand what is going inside the Android application, and a good knowledge of Java programming, because when you're designing for Android, there's so many built-in methods or predefined methods that you have to use. If you don't know how to implement the built-in methods and how to use them, it will become a lot harder to understand the Android application for design for Android application. Now, another knowledge that you need is XML programming. You don't have to know that much, because the way you learn Android, it is pretty basic and pretty simple. It use Android XML for layout purposes and the graphics, and it's pretty simple. Even if you don't know Android XML before, you'll be fine for Android application.
So when we're learning for Android, our main purpose was to communicate